Good morning. This is the ELP project submitted by Abhilasha Das, and the topic for this presentation is radio tuning and resonance. As we know, an LCR circuit is an electric circuit which consists of a resistor, an inductor, a capacitor in series or in parallel. In a purely resistive circuit, there is no phase difference between the current and the voltage. In a purely inductive circuit, the current lags the voltage by a phase of pi, while in a purely capacitive circuit, it is the opposite, and the current leads the voltage by a phase pi. The inductive and capacitive reactances are given by Xc equal to 1 by omega c and Xl equal to omega L. The net reactance is the difference between the two and is given by X equal to 1 by omega c minus omega L. The impedance of the circuit is the resultant of the vector for resistance R and the reactance X, and is given by Z equal to under root R square plus X square, where X is equals to 1 by omega c minus omega L. Resonance occurs in an LCR circuit because the energy stored in the circuit is stored in two different ways. In the electric field as the capacitor is being charged, and in the magnetic field as the current flows through the inductor. So the mathematical expression of the resonant frequency is 1 by 2 pi under root LC, and F is called the resonant frequency. The frequency, this is the frequency when the impedance is minimum. And for impedance to be minimum, both the capacitive and the inductive reactances should equal to each other. You will see the use of an RLC circuit and resonance phenomena in a tuning circuit, specifically the radio. What actually happens when we turn the knob of a radio or any other tuner? A simple radio circuit, as we can see from the figure, consists of capacitors, inductors, resistors, and diodes. When we tune the knob of the radio to connect to a particular station, what we are actually doing is that we are changing the capacitance of the capacitor in the LCR circuit. As the capacitance changes, the resistance also changes, and when the natural frequency matches with the resonant frequency, we are able to hear the sounds. How does a radio catch signals, and how can we scroll the knob to get different channels? A radio has two major components which help in this. The first one is the antenna. The radio receiver has an antenna to help it pick the transmitter's radio waves out of air. It is simply a wire or a metal stick, and it increases the amount of metal the transmitter's waves can interact with. The tuner circuit is the part of the radio which helps the antenna to separate one sine wave from the thousands of radio signals that it receives. So where does the resonance come in? The first part of the tuning circuit is the variable frequency oscillator, and the tuners work specifically on the principle of resonance. The knob on the face of the radio turns the plates of one side of an air capacitor while the other set of plates are static. This causes a change in the area between the two sets of plates. The capacitance changes, and this capacitor is a part of the LC circuit, and the values of L and C together decide the resonating frequency of the circuit. After the antenna has picked up the frequencies corresponding to these frequencies, a number of voltages appear across the series LCR circuit. However, the maximum current flows through the circuit only for that alternating voltage, which has a frequency equal to that of the resonating frequency. So by turning the knob on the face of the radio, we are changing the resonating frequency of the tuner by changing the value of C, and we are making it equal to the frequency of the desired radio station. In this way, the frequency of the desired radio station is accepted by the tuner of the radio. There is also another thing called the Q factor and selectivity. In case of the radio, such circuits are used to respond selectively to signals of a given frequency while discriminating against signals of different frequencies. The response of the circuit is more narrowly peaked around the chosen frequency. We say that the circuit has higher selectivity. A quality factor is a measure of that selectivity, and we say that a circuit having a high quality factor is more selective. So this was all about the basic idea on how a radio catches signals and plays them using the concept of resonance. Other applications of the LCR resonance can be seen in as a tuner circuit in television sets. It is also used in filters like low pass, high pass, band pass, and band stop filters. It is used as oscillators, voltage multipliers, and pulse discharge circuits. All of these circuit diagrams are given in this slide. There's also an interesting case of the Tacoma Bridge collapse, and its collapse is mainly linked to the phenomena of resonance. Generally, we can see that we can hear that a group of soldiers while marching on a bridge are asked to break their steps very often. And the rhythmic march, this is because the rhythmic marching can set extreme vibrations at the bridge's natural frequency. If the synchronized footsteps resonate with the natural frequency of the bridge, it can stagger the bridge apart. So when designing such structures, the engineers ensure that the resonant frequencies of the components are different from those of the other oscillating components. And the biggest example of this, as we have already mentioned, is the collapse of the Tacoma Bridge, in which the frequency of the air matched with the frequency of the bridge, leading to its collapse. So that was all about resonance in LCR circuits and other phenomena, and we can see that LCR circuits play a very important role in modern times. However, the phenomena of resonance should also be taken into consideration so that while designing structures, so that it does not turn into a catastrophic disaster. Thank you.